This recording is for Chapter 1, Section 1, Graphs and Equations. So everybody please be on page 70 in your textbook. Some of this you will recognize a lot from Algebra 1 and Algebra 2. Some of it a little bit more frequently seen than others. But in general, graphs of equations are sets of all the points that are solutions to the equation. Since it would be impossible to list all of the solutions, the graph is the only way to show them all. So when you're looking at a line on graph paper, every single minuscule dot that connects to make that line is an actual coordinate solution to the equation that was graphed. To find if a point is a solution to equation then, plug it into the equation for x and y and solve. True statements mean that the point is a solution. False mean that it isn't. So if we had this question that I put on this slide, is 2, -1 a solution to y is equal to 3x minus 7? You simply need to plug it in. So the y value of that point is -1. The x value of that point is 2. And now we solve. So -1 on the left, 6 minus 7 on the right. -1 equals -1 is the statement that we solve to, and that's a true statement. So then that means that 2, -1 would in fact be a solution to the equation given. Graphing lines using the point plotting method. We often refer to this as making a t-table or making an xy table. So if you turn to example number 2 in the textbook, it's at the top of page 71. Sketch the graph of y is equal to -3x plus 7. You get to randomly, on the point plotting method, you get to randomly choose your x values. Now, depending upon the equation, there might be better x values to choose than others. For example, if you notice in the equation that you're going to be multiplying a fraction like 1/4 times your x, well, it would be smart to pick numbers for x that multiply nicely by 1/4. Things such as 0 or 4 or -4 or multiples of 4 and so on. Okay, otherwise you really truly are free to put in whatever you wish. This table in this example has 6 points that they found. Generally, rule of thumb when you're doing the point plotting method, do 3. If you have 3 points that in fact line up in a straight line, you can be pretty sure that you have graphed your line in the correct place. If you only use 2, you can draw a straight line through any 2 points. If you can get the third one to line up as well, now you have kind of a guarantee that you are correct. Now, example 3 in the text has you sketch a graph of a quadratic equation. All right, those are the ones that have the x squared term in it. Remember that these are going to end up making parabolas. So if you look at the end graph that they have for us on page 72 underneath the table of values, you can see that it does in fact form a parabola. Now, nowhere in this example does it remind you of how to find the vertex of the parabola. Now, the vertex, remember, is the maximum or minimum point in there. So they found 0, -2, which is the vertex. But you could find or come up with 10 or 15 points and never end up finding where it's going to actually make that bend. So if you go back in memory to your Algebra 1 and Algebra 2, we use -b over 2a to find that first x value that you want to plug into your table, just to make sure that you find the spot where that parabola is going to curve. Okay? Remember that a and b come from the coefficients in the equation. So when you're looking at the graph at the top, that y equals x squared minus 2, the value for a is the coefficient of the x squared term. For that particular example, it would be a 1. Notice that there is no regular x term in there. That would indicate to you that the coefficient of that must have been a 0 in order to wipe it out. So your vertex would be found at 0 over 2 times 1, or 0. And that's why 0, -2 does end up being the bend of that parabola. So in your notebooks, probably being we're going to be doing some graphing of these parabolas by hand, not on your calculator all the time, you should probably make this special note that to find that middle value for your vertex, use negative b over 2a. Another thing that's talked about starting at the top of page 73 are the intercepts of a graph. Intercept is just a fancy word for crossing. So where does the graph cross the y-axis or the x-axis? Now, why do we even need to find these things? Well, as we get into finding solutions of graphs, you're going to be looking for those intercepts, the x-intercepts in particular, because those are going to be the solutions to your equations. So for example, if we were graphing a parabola and it crossed the x-axis like the one on the previous page did, we can find the solutions to our parabola simply by looking at a graph of it. So in the future, whether we do it by hand or do it on a graphing calculator, if we find those x-intercepts, we have the solutions to our graph. We also will be looking at using quadratic formula to find those solutions, but if your graph ends up on nice spots, it's maybe every bit as fast rather than to plug stuff into quadratic formula and solve it that way. So that's the need for knowing what intercepts are and what they do for us, and they're very easy to find. Okay, if you want to find the x-intercept and the y-intercept, notice that all you do is put, oh, I'm jumping ahead of myself here. We're going to go off of pictures to start with. Take a look at example number 4. They're identifying the intercepts on this picture, and you just have to look at it. If you look at example number 4, first of all, the x-intercept obviously crosses at -1, 0, and the y-intercept crosses then at 0, 1. Okay, they have a parabola down below too where you're finding your intercepts. The x-intercepts would be -5, 0 and 0, 0, and the y-intercept would again be the 0, 0 point. So that time the x-intercept and one of the x and the y-intercept end up being the same point. In the future, if you were simply given an equation and asked to find the intercepts, all of the x-intercept points, okay, if you look at any of them that are on that page 73, notice that the coordinate for y is always 0 because you're on the x-axis, so you didn't move up or down when you graph the point. So if you are simply looking for the x-axis or the x-intercepts given the equation, plug 0 in for y and solve. Vice versa then, if you were finding y-intercepts, put 0 in for x, because again you want the point that's on the y-axis, not left or right at all, so the x value of the point is 0, always. Now, the example on page 73, I just did that. Symmetry is another thing that we're going to take a really quick look at with this chapter, and they're really only giving it to us as a tool, excuse me, to help make graphing go faster. If you can look at an equation and run a couple of fast symmetry tests, you only have to find half as many points. Because if something is symmetrical, when divided in half, each half lines up perfectly with the other half. So if we're looking at a quadratic equation, we can figure out if it's going to be symmetrical along the x-axis or symmetrical along the y-axis, and then just find out half of it and duplicate the other half on the other side of the axis. So it's not always a necessary thing that we be able to test for symmetry, but it could be a real time-saving factor. So take a look at the bottom of page 74, and I've kind of summed it up on this next slide here. To check it if equation has symmetry, do the following things. So if it happens to be symmetrical around the x-axis, you can sub -y in for y, and you're still going to end up with the same equation. Testing to see if it's symmetrical along the y-axis, you're going to sub -x in for x, and still end up with the same equation. Now, origin symmetry, this means you could or you need to put in both -x and -y for their positive counterparts and get the same equation. All right, that sounds a little bit confusing, but if you look through example number 5 at the top of page 75, you can see this in process. We're also going to do one of these together. Here we go. Right under example 5 is the checkpoint that says test y squared equals 6 minus x for symmetry with respect to both axes and the origin. Okay, so the equation itself, very simple. It is a quadratic because we have a squared variable. Y squared equals 6 minus x. So let's test this for x-axis symmetry first. So for x-axis symmetry, we're going to put negative y in where we saw positive y. Now, what is negative y times another negative y? Y squared. Now notice that that's exactly the way the equation looked at the beginning. So putting negative y in there did not change how our equation looked. So we do have x-axis symmetry. Let's do the y-axis test. That again from the previous page said, excuse me, you plug negative x in for x and get the same thing. All right, so leave this alone, 6. Now we're going to subtract instead of positive x, a negative x. Simplify. Negative negative is plus. Does that look like it did at the beginning? No. No y-axis symmetry. Origin check. Now we're going to put the negatives in for both of them. So put the negative y in and the negative x in and simplify. That does not look like it started. We have a plus x rather than a minus x. So no symmetry around the origin. But if we were to graph that parabola, it would be symmetrical around the x. So again, if you notice that, or if you did this quick check, it doesn't take very long, you'd be able to graph it in maybe half the time, because you would need to come up with half the number of points. Circles are another part of this first section. You guys have worked with circles before. The equation for a standard form of a circle is not all that difficult. X minus h squared plus y minus k squared is equal to r squared. H and k are the center of the circle. Okay, so if we were to take those numbers out of the equation that we have, it would give us where the circle center lies. And then r, of course, very logically is going to stand for the radius. So in the formula, you've got radius squared in there. There is a problem in your book that's completely done out for writing the equation of a circle, example number 8 at the bottom of page 76. We're going to do another one. We're going to do the checkpoint that sits right underneath that. So if we had a point on the circle of 1, negative 2, and we're told that the center of the circle was negative 3, well that should read negative 3, negative 5. Hang on, I'm going to fix that. There we go. Write the equation of the circle. All right, well, we don't have the radius given to us. So that's one thing that we're going to have to find first. Now, if you think about this, and we know the center, and we know a point on the circle, our radius is going to be the distance from the center to that point on the circle, right? So distance formula is the first thing that we're going to work with. So distance formula, remember, was x2 minus x1. So I've got a negative 3 minus 1, and we square that, plus the y minus the other y squared, and then we take the square root of that. So start solving. Negative 4, and if we square negative 4, we get a positive 16. Inside the other part, remember that minus a minus is going to turn to plus. We end up negative 5 plus 2, which is negative 3. Square it, we get 9. So the distance, or our radius, is the square root of 25, or 5. So using our formula for the equation of a circle, oops, don't want that. We have x minus h squared plus y minus k squared equals r squared. So the center, they said, was -3, -5. So that's h and k. So x minus a minus 3. Y minus a minus 5. And then we just found our radius was 5, so r squared is going to be 25. And there's the standard form of that circle as an equation. So that's not such a terrible one to work with. And that's all I have for you to go through. There is an application problem on page 77 that has you making a table of values and reading it to make a graph and to make some inferences. There will be something in your homework that is similar to that, so you may want to refer back to number 70 or page 77 to see how that's all set up and laid out. But I was not going to take your time right now to go through another one other than what's in the book already. So notice that the assignment this time, just because we are now into accumulating points for your college grade, we are doing evens. So be sure, if you need to, come in before school, ask me some questions. We'll be doing less of it as an open group in class, I would imagine, just simply because I'm not going to do your homework for you. So please feel free, though, to come in on your own and give some of these a try tonight, so you've already got questions in line for you when you get to class. All right, see you guys in class.